Today, we're going to continue looking at integration by substitution and integration by parts. We learned a few tricks for substitution. We learned a few tricks for parts. And I want to go back to a trick that we've used, but only once, and that's integrating by differentiating. So a great example of this is the integral of arctangent. The first step is to decide, well, the 0th step is to make sure that we don't have a substitution. And there's just not much to substitute here because there's arctangent and then that's it. If it was like if there was an x squared, then we could substitute that, or if the derivative of arctangent was somewhere around here, but there isn't. So we switch to parts. The first step in parts is to decide on u and dv. So in this case, we've only got one. It looks like we only got one part. That's not just the constant 1. So we have this arctangent. I don't want to put arctangent in dv because if we knew that, then we wouldn't be doing parts. We would just be writing down the antiderivative of arctangent. So the only place for arctangent to go is in the derivative slot. That leaves only the dx to be in the dv slot. The next step is to get the two parts that we need to find. So differentiate u to find du. So here the derivative of arctangent is 1 over 1 plus x squared plus 1 dx. So the derivative of arctangent is 1 over x squared plus 1. That's just one of our derivatives that we just have to remember all the time now. And the antiderivative of 1 is just x. Now we're ready to put things together in the parts formula. So according to parts, the integral of arctangent is uv, so x arctangent x, minus the integral of v times du. So that'll be x over x squared plus 1 dx. After we put everything into the parts formula, the next step is to do our secondary integral. And in this case, we see an x squared in the denominator and an x in the numerator. So this suggests that we're going to be doing a substitution where w is x squared plus 1, and that's been plugged into the 1 over x function. So that indicates that what we're actually going to be integrating is 1 over w. And then we need to make sure that we have, and this x in the numerator is going to be the dw. So if w is x squared plus 1, then dw is 2x dx. So the x dx is going to be a 1/2 dw. So x squared plus 1 is going to be our inside function. 1 over w is our outside function. And then the x dx is just all going to be the dw, or 1/2 of a dw. Now keep in mind, this is just this secondary integral. So we still have x arctangent x and now we can integrate, let's write the w integral for x over x squared plus 1. So there's going to be a 1/2. I can put that out in front. The integral of 1 over w dw. Now we just need to integrate the 1 over w. The integral of 1 over w is natural log of w, since we can't do the add 1 to the exponent business. So I have x arctangent x minus a 1/2 natural log absolute value of w plus c. And we can write the plus c at this point because we have done the integration part. Then the last thing we'll need to do is replace the w with its expression in x. So we'll have x arctangent x minus 1/2 times the natural log of x squared plus 1. In this case, I can drop the absolute value signs for parentheses because x squared plus 1 is always positive. And there's our antiderivative of arctangent x. And we got there by using parts, and we got there by actually differentiating the arctangent. So in this case, we can drop the absolute value signs because x squared plus 1 is always positive. So since the x squared plus 1 is always going to be positive, we don't need the absolute value symbols anymore. We can just put it in parentheses. One of the things that we want to notice about this is that this relies on the derivative of arctangent is 1 over x squared plus 1. And this gives us a route into integrating. This gives us an integral statement as well. So the derivative with respect to x of arctangent x is 1 over x squared plus 1. This is just one of the derivatives that we have to remember. But it tells us an antiderivative as well. So this means that the integral of 1 over x squared plus 1 dx is arctangent x plus c. That's just the relationship between derivatives and integrals. So the derivative of arctangent is 1 over x squared plus 1. So the integral of 1 over x squared plus 1 is arctangent plus c. So one of the things that we noticed in this problem was that the integral of x over x squared plus 1 dx was a 1/2 natural log of x squared plus 1 plus c. So that's what we got out of this one. So we started off, we have a constant over x squared plus 1 that gives us an arctangent. We have an x over x squared plus 1 that gives us a 1/2 natural log of the x squared plus 1. Let's think about what would happen if I raise the numerator 1 degree higher. So let's see what we need to do here. We've got x squared over x squared plus 1. We could try a substitution, but if w is equal to x squared plus 1, then I need one factor of x to be the dw, but there are two factors of x. So that substitution, we have too much stuff going on. Oops, let's do that here. So the substitution w equals x squared plus 1. What we need to make this go is an x. So 1/2 dw is equal to x dx. But that raises the question, what are we going to do with this extra x? So one factor of x is the dw, but what's the other factor of x going to be? Well, let's just say what about? We could try solving our expression here for x, but it's going to introduce square roots, and we know that that can cause problems. So we could say that x is subtract 1 and take the square root, plus or minus the square root of w minus 1. But we don't want to introduce square roots into our integral, because I have a square root of w minus 1 over w. And we didn't really make good progress. So fortunately for us, we're going to, when we have an x squared in the numerator above another x squared, we're going to reduce the problem to the previous problems. So what we're going to do is we're going to rewrite. So we're trying to integrate x squared over x squared plus 1 dx. So what we're going to do is we're going to think of this as 7 over 3. 7 over 3 is inconvenient, so we're going to write 7 over 3 as 2 1/3. And we can get there by dividing. 3 goes into 7 2 times. 2 times 3 is 6. 7 minus 6 is 1. So 7 divided by 3 is 2 1/3. We're going to do the same thing with x squared over x squared plus 1. We can do the division because the degree of the numerator is greater than or equal to the degree of the denominator. So I'm going to divide x squared plus 1 into x squared. And we're going to ask the same questions that we did over here when we wrote our improper fraction as a mixed number. We said 3 goes into 7 2 times. That's just the incantation that I was programmed with when I was a kid. But what I know now is that we're asking the questions, how many times can we subtract 3 from 7 without going negative? It's actually okay if we do go negative, but the fractions look weird. So how many times can we subtract 3 from 7 without going negative? That's twice, because 2 3s is 6 and 7 minus 6 is 1. No more room to subtract any more 3s. So we'll ask the same question over here. How many times can I subtract x squared from x squared? I can do that 1 time. And then what we did here, 2 times 3 is 6. So 1 times x squared plus 1 is x squared plus 1. And then we subtracted. So we'll do the same thing over here. We'll subtract. That'll result in 0x squared. And 0 minus 1 is minus 1. That's our remainder. So x squared over x squared plus 1 is equal to 1 minus 1 over x squared plus 1. The reason that this is progress is that I know how to integrate 1 over x squared plus 1. So we can rewrite our integral as the integral of 1 minus 1 over x squared plus 1 dx. And then I could just separate this into two integrals, integral of 1 dx minus the integral of 1 over x squared plus 1 dx. The integral of 1 is just x. The integral of 1 over x squared plus 1 is a 1/2 natural log of x squared plus 1. So in this case, if we have all we needed was 1 over x squared plus 1 and x over x squared plus 1. Because if the degree of the numerator is higher, is 2 or more, then we can just divide and the remainder will have a degree less than 2. In the same way that we can write an improper fraction as a mixed number, we divide and then the remainder will be less than the denominator. So all we need is the integral of 1 over x squared plus 1 and the integral of x over x squared plus 1 . And if we have a degree higher than 2, if the degree of the numerator is 2 or more, use long division. And you'll have a polynomial plus a 1 or an x over x squared plus 1 dx. So anything where the degree is 2 or more, we can just do the long division to break off a polynomial, and then the fraction part will either have a 1 or an x in the numerator, or a combination of both, which we could also just split. Any questions?
Professor, could you move it up a little bit?
Yes.
I'm kind of confused to like the 1 to like -1 over x squared plus 1 part. Is it 1 minus 1 over x squared plus 1 or?
1 minus this here?
Yeah, I know
It's
I
1.
know the 1's coefficient, right?
That's not a coefficient. That's a
Is it not?
constant term. We're
Okay.
subtracting this fraction. This is the whole number part 1 minus, and then the remainder is -1 over x squared plus 1. Just like we do with numbers. We say the whole number part is 2, the remainder is 1, we put that over the 3. So we put the -1 over the x squared plus 1. And they're separate terms. Just like when we write 2 1/3, these are separate terms. This means 2 1/3. So the 2 is the whole number parts, and then we're adding that fraction of 1/3.
Okay, so then how did you get like the 2 integration right below that?
This one here,
Yeah, like 1 dx minus integration of like
the integral
x.
of 1 is x. That's one integral. And then this is the integral that we did on the previous page.
Right.
W is x squared plus 1. dw is a, oops, this is a 1 over x squared plus 1. I did the natural log, and it was supposed to be the tangent. I put the natural log one instead of the tangent one. The integral of 1 over x squared plus 1 is arctangent. So I got the natural log part wrong. I was doing wrong things. I read things wrong when I wrote that.
Also, could I ask for clarification on like how come we're integrating one?
Because I'm rewriting this fraction, x squared over x squared plus 1. I'm replacing that with 1 minus 1 over x squared plus 1.
Oh, okay.
So then I can just integrate each term.
Like separately?
Yeah.
Okay.
So a lot of times we just say, here's an integral and here's another integral, and then we just leave it at that. One of the reasons that we can stop stop the numerator from going up, because it's anything more than 2, we can just use long division. Long division will break off a polynomial. That'll be like the whole fraction part will still have an x squared plus 1. But if we do our long division right, the numerator will be either a constant or an x. That'll make the degree 0 or 1. So we can always do this. We can rewrite our improper fraction where the numerator is greater than the denominator by writing a whole number, and then the remaining fraction will have the numerator less than the denominator. So we think of the size of the polynomials based on their degree. And the long division process that we do for polynomials is the same long division process that we do with regular old numbers. We usually phrase it kind of badly because we say 3 goes into 7 2 times, but that question is really, how many times can we subtract 3 from 7 without going negative? The funny thing is, we really can't get this wrong. When we set up division this way, we're just trying to see how many times we can subtract 3 from 7 without going negative. So let's suppose I try to subtract 3 from 7 3 times. 3 3s is 9, and 7 minus 9 is -2. So this doesn't look right. But if we take the whole number part of 3, and the remainder is a -2, instead of 2 and 1/3, we have 3 and -2/3. But 3 and -2/3 is just 2 and 1/3. So we didn't get it wrong. We're just writing it in some messed up way with subtraction. And still, so this is if we overshoot it, it's no problem. We'll still have the right amount. We just subtracted too many 3s. We subtracted 3 3s when we can only subtract 2 3s. If we subtract too few, if I just subtract 1, we end up with 4. And at this point we say, oh, we can subtract another 3. So, and what did we do? So we say 2 times 3, we do 7 minus 6. That's just 7 minus 3 and then minus 3 again. And I have subtracted 3 from 7 twice with 1 left over. So that's the thinking that's going on behind this. And we want to be able to think that way so that when we have to do this with polynomials, we think of the same way. We think, how many times can I subtract x squared from x squared? I can do that 1 time. And so if I have a different division problem, if I have, say, x squared plus 1 dividing that into x cubed, we think, how many times can we subtract x squared from x cubed? To even be able to do this, I have to multiply by x. X times x squared is x cubed. X times 1 is x. In order to be able to subtract x squared from x cubed, I have to multiply by x so that they'll be like terms, and then I can subtract them. And 0x minus x is minus x. And then once to subtract x squared from x, I'd have to subtract a fraction, so I'm not going to keep going there. I'm going to say x, the numerator of the fraction part is now less degree than the denominator. So I can say x cubed over x squared plus 1 is x minus x over x squared plus 1. Same kind of thinking. How many times can I subtract x squared from x cubed? And that's x times, because x times x squared is x cubed. That makes them like terms, and we can subtract. Any questions? These two are good foundational integrals to just remember. You don't have to memorize them, you just have to remember them. All right, that's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.